Hi, this is ET250, Lecture 17. Today we're going to talk about transformers and mutual inductance. We'll look at very briefly the ideal transformer equations. This is under ideal conditions. V2 equals N2 over N1 V1, and I2 is just the opposite ratio. Then we're going to also look at what happens if you don't have ideal conditions, and that's where we have the mutual inductance equation. It's a little more complicated. So V1 is dependent on the derivative of its own current and the derivative of the secondary current times this mutual inductance. And then V2, the voltage on the secondary side, is equal to the derivative of its own current and the derivative of the primary current. Okay, and then this mutual inductance, guys, looks very similar to the regular self-inductance equation, but there's also a few more forms of the same equation. These are all equivalent. To determine these signs here, we'll introduce this concept called the dot convention, go over a few examples, and then look at a simulation. All right, so let's begin. So what is a transform? Well, and what does it do? So a transformer, this is what a transformer looks like. And what it can do is step up and step down AC voltage and current. And so here we have a transformer core. And what do we see inside? We see steel, laminated sheets of steel, and we see copper. And this is a multi-tap transformer. But if you were just looking at the bare basics of what we're going to be studying right now, it's just 4 leads. Here, there's a lot more than 4 leads. But the idea would be you have a primary coil and a secondary coil. The other thing a transformer can do is it can electrically isolate circuits. And let's look at that from the construction, right? So I have a primary coil, secondary coil, and this core is made of high permeability material like this, right? So that's where the steel comes from. And then you see the copper windings here. These copper windings are the coils themselves. Now they are insulated relative to each other. Okay, so don't just think that these copper coils are bare copper and touching each other. Nope, they actually have a thin layer of insulation. Here's an example of that same kind of copper coil. It looks like it's bare copper, but it's not. It actually has a thin coating of enamel around it, right? And that way the current's forced to flow around and around and around, not just go here and then finish off, right? So that is the construction of a transformer. Now, the reason why this transformer here is in this shape and not shown here is because what you have is kind of like an 8 on its side, right? So there's a middle bar, and that 8 configuration allows the magnetic flux to flow around and back into a loop, okay? So this high permeability material is a path or a conductive path for magnetic flux, whereas the copper is a conductive path for electricity, all right, and current. Okay, so what are some relevant parameters here? Well, you got N1 and N2, those are the number of turns of each side. And you have what we'll call as M, the mutual inductance, and you have its own self-inductance L1 and L2. So these are some of the relevant parameters when looking at a transformer, okay? All right, so if everything is ideal, we will use, well, and in any case, what is ideal or not ideal, we will use this symbol. It's just 2 inductors put side by side like this to denote our transformer. And if it's ideal, what you can do is just look at the turns ratio, N2 over N1, where N is the number of turns, and you get this voltage relationship. So if N2 is a bigger number, so I have 10 turns here and 1 turn here, what happens? I get a 10-to-1 ratio on the secondary. So this is actually going to be bigger than this one by 10 times. And the ratio is what matters, okay? We will see that the L and the permeability does affect the transfer, but these are under ideal conditions. Now the current is going to be the opposite ratio. Notice the ratio flips. So we have N1 over N2. And this, like I said, only works under ideal conditions. We assume AC current and voltage, and it will not work with steady state DC. So if I just have 10 volts constant, I'm not going to induce anything on the other side here. Now you see this plus or minus, plus or minus. We will use this new thing called the dot convention to determine sign. And what the dots inform us is the relative winding of these coils, right? And we won't talk about how to set up the dot convention to the next lecture, but we will use the dot convention to show us how it determines the sign, okay? Today's lecture, I just want to go into like an introduction. Okay, so what happens if things are not ideal? Well, we have this other set of equations, and these are what we will call the mutual inductance equations. Maybe I can even put it here. Mutual inductance equations, right? Whereas these are the ideal transformer equations. All right, that way we have a name for these sets of equations. So mutual inductance equations, ideal transformer equations. All right. Now, this works even under non-ideal conditions, right? This one you have to assume ideal. And notice you still have the plus or minus, but now you can see that this voltage here is dependent on its own derivative or current derivative and the other side's current derivative. And this voltage on this side is dependent on on its own derivative here and the other side's current derivative. And notice the pattern: 1, 1, 2, 2, 2, 1. L1, L2. And the M, the mutual inductance, is the same for both. Okay, it's the same for both. If we go back over here, look at this one, V2 to V1 with this ratio, I2 to I1 with the same ratio but inverted. So there are similarities. In fact, we will show in the next lecture that this actually comes from this under ideal conditions. So this is a special case of this one. This is the more general equations. This is just the special one, all right? Okay, so let's study this one for a bit, and then later we'll prove in next lecture that this is from this. Okay, so L1 and L2 is the self-inductance. We already know this. This is just like a regular single inductor, no problem. M is the mutual inductance. And the sign of the self-inductance, well, we've already done that, passive sign convention, same as Ohm's law, capacitor, power, inductor, right? All this stuff, right? We've done it before. Now for the sign for the mutual inductance, again, we're going to use this dot convention. And in both cases, the dots inform the relative coil winding, okay? So this dot convention will come up. All right. So let's look at this M. And I do really want to hit home that this M here is magnifying that the opposite current or the opposite change in current is affecting the primary voltage, and vice versa. The opposite change in primary current is changing the secondary voltage, right? The bigger the M, the more induced effect, right? And so here we go. We have the time derivatives. Notice because you have time derivatives, you have to have an AC-like current. If it's steady state, these derivative terms go to zero, right? So I hope that shows that AC is the name of the game here. Okay, so let's look a little bit closer at this M term. And now you can recall if you had just a plain old inductor by itself, you have some number of turns, you have L is the stack height, A is the cross-sectional area, and mu is the permeability of whatever core you're using. This is how you would affect the inductance, okay? And so M equals K mu N1 N2 A over L. Look how similar these two equations are. You have a mu, you have an A, you have an L, and instead of an N squared, you just have N1 and N2, which is related to the number of turns on both sides of the transformer, right? Now this K, that is what we call the coupling coefficient. And that K is a value between 0 and 1. And you can imagine 1 would be perfect ideal conditions. Now, as K gets closer to 1, we will call that tightly coupled. And as it gets less closer to 0, it's called loosely coupled, right? And so an example of a loosely coupled system would be like a wireless cell phone charger. In fact, I have one right here. So this is my wireless cell phone charger here, okay? Yeah, my cell phone, and there's a coil in here. That would be the primary coil. And there's a secondary coil actually in my cell phone, and I can wirelessly charge my cell phone, which is really neat. Over here, this is on the tightly coupled side. You're gonna have, for an example, a steel power transformer. Maybe something similar to this, right? Or bigger, right? And you're going to get better and better coupling, a K closer and closer to 1 for something like that, okay? Now, in this assumption for this equation, we are assuming that in both coils, the mu, the cross-sectional area, the length, they're all the same. You kind of see that in here, right? It's, in this case, they're wrapped around the same coil, right? Or sorry, the same branch of the steel. So they're the same stack height. And so all these things in the same cross-sectional area. So here you're getting this kind of equation. Now, if you had two coils drawn like this, on the what do you call it, on the first page, then it depends, right? Then it depends. This is, by the way, not the best design, right? But I draw it like this just to, it's easy, right? Okay. So what are some other forms? Here's a few more forms of the mutual inductance, right? And so it's actually what the square root of L1 and L2. I believe this is called the geometric mean, right? It's like an average, right, of L1 and L2. So square root of L1 times L2, right? Another way to write it is if I know the ratio of the turns and I just know L1, well, I know L2 is dependent on this ratio in L1. So this is another way to write it. And vice versa, I could write K times L2 times N1 over N2. Notice the ratio flips from these two. So what's the moral of the story? If I have less L and more K, mu, N1, N2, or L1 and L2, I will get more M. I'll get a better relationship between the opposite change in current and the primary voltage, and vice versa, right? So more M means a better transformer, right? More M means this to this is magnified, okay? And these are the physical parameters that relate the di dt to the V. Okay, and so if you're looking at the big power transformers, you can see, you can't really readily see it here, but you can maybe see it in these different forms that I might need a big inductance, right? Okay, notice how this inductance doesn't necessarily show up in the ideal transformer relationships, right? This wouldn't tell you that, hey, it's, you know, if I have, let's say, a 10-to-1 ratio and I have 100 turns to 10 turns or 10 turns to 1 turns, this would say, I have no idea what the difference is, right? Because all these terms don't pop up. We'll see later that actually it matters. It does matter. And your transformer won't behave as well if I have too small an inductance. Okay, interesting. Okay, let's keep going. So how would I show these are true? What I could do is I could look at this one and I say, well, can I plug in my self-inductance equation and see if I get that? Well, it's not too bad. Mu n1 squared a over L, mu n2 squared a over L. If I multiply them together, I just get this guy, right? So notice I'm getting a mu squared, an n1 squared, an n2 squared, an a squared, and L squared. If I square root everything, boom, I just get that. Very simple to show, right? So this shows us that 1 and 2 are the same. Of course, you're assuming that the a, the mu, the L are all the same. Okay, what if I want to show that this and this is the same, right? Okay, or this and this are the same. Well, what I can do is I can take these two equations and divide one by the other. And you can see if the mu's are the same, the a's are the same, the l's are the same, they all cancel out and I just get n2 squared over n1 squared. That's not too bad. All right, so that means that L2 is n2 n1 squared L1, right? If I just pull this over, or L1 equals n1 squared n2 squared over L2. I could just take these two guys and plug them into here and I get two different versions. I get these versions, right? So I plug, let's say I plug this version in, right? You can easily see things are getting they're getting, squared, right? L1 squared, N2 squared, N1 squared, square root, I get this version. Or if I take this version, plug it into here, I get an L2 squared and I flip the ratio, right? So pretty easy to see that all four of these are equivalent, assuming that mu, A, and L are the same. Okay, not too bad. Okay, let's keep going. So the next question is, what do the dots tell us? What do the dots tell us? So remember we have these dots here. And so what it's saying is if I can increase charge on the primary dot, it'll increase and induce a charge on the secondary dot, okay? So here's an example, I have two dots. So if I'm increasing the charge here, I'll increase the charge on this side. Now here's a different version where the dots are diagonal. If I increase the charge here, I'll increase the charge on the bottom side, right? Okay. And so how would I increase the charge on the primary side? Well, I can either send current into the dot, or if I had a voltage, I could increase the voltage here at the dot, okay? So I can either send current in or increase the voltage, and that's going to induce positive charge at these dots, okay? All right, so let's look at an example. Let's say I have an I1 and a V2. I have a current direction, a voltage polarity, right? And so here, let's say this is the primary, this is the secondary for now. If I increase I1, a positive charge is going to build up. And if a positive charge is building up and I'm reading V2 with the positive terminal coincidentally at the dot, I would read a positive number. And so just a note, just remember I1 is going into the dot in this case, and V2 positive is touching the dot. And so what do we see? Well, if we were to write down half of our mutual inductance equations, we would V2 equals itself, or the self-inductance. And because this V2 would read a positive, I would put a positive here for increasing I1. Right? I hope that that is consistent with what I just said over here. Okay. So I'm increasing here. You can see I'm increasing the charge here by sending current in. I'm inducing a positive charge on the secondary. And imagine this is like a multimeter. My V2 is going to read a positive number. Good. Now let's look at another case. Let's say we have the same situation with the dots are on the top. And now let's say I have an I2 leaving and I have a V1 on this side. Now let's look at what happens. Notice that I2 is actually leaving its dot. So if I2 increases, what happens? A negative charge builds up because this I2 is leaving, right? It's kind of the opposite case of here. But notice the V1 positive is still touching. Well, if I'm measuring this V1 like a multimeter, what's going to happen? This is going to read a negative number, right? V1 would read a negative number. And so that means if I wrote down the other half of our mutual inductance equations, look, V1 equals its self-inductance minus M di2 dt. So an increasing I2 in this case would lead to a negative V1, and that's why you see the negative there. Okay, so I hope that intuition is nice. Okay, note again, I2 is leaving the dot and V1 positive is touching the dot. Kind of opposite this case where I1 enters the dot and V2 positive touches the dot. Okay, so if I were to summarize what I just did, right? This is essentially these two things. Notice I have V2 with the positive here, I1, and I have I2 leaving the dot in V1. If I were to write out the full mutual inductance equations, I would get this. V1 equals, I'll just look at the mutual inductance, minus M di2 dt, that's what I have over here, plus M di1 dt, that's what I have here, okay? Now the self-inductance is easy, right? In this case, I1 is entering the positive terminal, so that's positive, and I2 is leaving the positive terminal, so that's negative. And note here, I restated it, I2 leaves its dot and V1 positive touches the dot. So you're looking at opposite current and voltage for the sign of the mutual inductance. Here, I1 enters its dot and V2 positive touches its dot. Boom, and we get a positive. Okay. So maybe we can summarize these in a set of rules. Okay, so here's the rules you can remember. The dot convention rules for sign. So yes, you have yourself and plus or minus. How do you determine this plus or minus? So if you're looking at V1 and I2, you say if I2 enters its dot and V1 positive touches its dot, or if I2 leaves its dot and V1 negative touches its dot, use the positive. Okay, otherwise use negative. That's essentially what this one was doing, right? In this case, I1 and V2 positive were touching this dot. It's the same rules for this one, right? If I1 enters this dot and V2 positive touches this dot, actually that's this one, use the positive. If I1 leaves and V2 negative touches dot, it's equivalent, right? Okay, so notice in this one, let's see if that matches our rules. I2 leaves the dot, okay, we got this one. And V1 negative touches dot, oh, but V1 positive touches, so we're gonna use negative. Okay, so good. These things are matching the dot convention rules. Okay, not too bad. So let's just do a bunch of examples and just make sure that we are consistent. So let's see here. So let's just, before we even, what do you call it? Write down the equations. What do we have? V1, V2, dots on the bottom, I1 going this way, I2 going that way. All right. So in this case, the self-inductance, I think in both sides are positive. I1 enters the positive terminal, I2 enters the positive terminal. Okay, yay. Okay, so we're getting positive and positive. Okay, let's follow this one. I1 is, or let's do the I2 first, because I believe I2 is on the corner. I2 is leaving the dot. If we follow through here, it's leaving the dot. Okay, since I2 is leaving the dot, we can follow this one, and V1 negative is touching this dot. We follow, oh, we're going to use positive. Let's double check. Excellent. Okay, what about this one? I1 in this case is leaving the dot and V2 negative is touching the dot. I1 is leaving the dot and V2 negative touches the dot. Use positive as well. So this is this is like a positive all around case. All right, let's go to the next one. Okay. What do we have here? Self-inductance, easy. I1 goes in the positive terminal, positive. I2 goes in the positive terminal, also positive. Okay, good, good, okay. Let's look at the I2 case. I2 is leaving and V1 positive is touching. Oh, that's going to be negative. Good. I2 leaves, V1 positive touches. Okay, what about this one? I1 enters, but V2 negative touches. Oh, that's also going to be negative. Good, good, consistency. All right, let's keep going. What's next? Let's look at the self-inductance. I1 goes in the positive terminal. Oh, that's positive. I2 leaves a positive terminal. That's negative. Excellent. So we're getting positive and negative. Great. Okay, let's look at the dot convention. I2 is leaving the dot. V1 positive is touching. That's going to be a negative. Yep. And what about this one? I1 enters the dot and V2 positive touches. That's going to be a positive. Excellent. Okay, let's do one more. What do we got here? And in this case, we have self-inductance positive. I2 is leaving. That's negative. Good. And now mutual inductance I2 is in fact entering the dot and V1 positive is touching. So that looks like it's a positive, easy. And I1 is entering the dot and V2 negative is touching. That's negative. Perfect. Okay, so all these are consistent with these rules. Not too bad. Okay. Here's another example. Set up the mutual inductance sign strategy, put I1, I2, but then replace replace with one I, since KCL I equals I1 equals I2, right? This is kind of tricky, right? Because you have both transformers connected together under the same branch. So it's like they're in series, but also they're kind of connected, right? A little bit confusing, but I think we can work it out. So let's say the original problem didn't have I1 and I2. What we could do is we could set up dummy I1 and I2s that happen to be in the same direction of I, solve it with the regular mutual inductance, and then substitute that I back in. All right, so let's see how to do that. Okay, so let's look at the self-inductance. V1, I1's going to the positive terminal. V2, I2 is going to the positive terminal. So those are positive. And now let's look at this one. I2 enters its dot and V1 positive touches. Good, that's positive. And I1 enters its dot and V2 positive touches. That's also positive. So this is like a positive all around case, right? This is actually similar to this one. The only difference is we've connected, we've connected in this case, the negative to the positive. It's like we've drawn a line there as well, okay? And so once we're done, we can replace everything with I, right? That overall I. And look, these distribute out. It's almost like we've created a super inductor, right? V1 equals L1 plus M di1 dt, and V2 equals L2 plus M di1 dt, right? Kind of a super inductor kind of situation, right? Okay, let's look at another example. Okay, what happens if you have a similar thing? You've only switched the dots, which is kind of like you've changed like how you wound the coils. All right, we could do the same thing, the same process as before. Okay, self-inductance looks like it's all positive again, right? Because I1's entering V1 positive, I2 is entering V2 positive, right? And now we can look, okay, I2, what is it doing? It's leaving the dot and V1 positive is touching. Now it looks like a negative to me, right? I2 is leaving its dot. Okay, good. And what is I1 doing? I1 is entering the dot and V2 negative is touching the dot. That also looks like a negative. Yep. Okay. And then here, it's kind of like if you replace everything with I, it's like you've decreased the overall self-inductance in some way, right? Because you have L minus M, L2 minus M. All right, but not too bad. Okay, what is next? So Maybe a question is, are these the same? And yes, they are. If I have 2 dots on the top and 2 dots on the bottom, they're the same. If I have 2 dots on the diagonals, it's also the same behavior. And so what we can do is actually do an example where we have 2 dots on the top and the bottom. Let's just see it. So we saw this example before, right? Let's just run through it again, doesn't hurt. So what do we have? Self-inductance, positive, self-inductance, negative, good. And we have I2 leaving the dot and V1 positive touching, that should be a negative, okay? And we have I1 entering the dot and V2 positive touching, that's a positive. Good, that's consistent with what we got before. Now let's say we do the same thing. We haven't changed V1, V2, I1, I2, right? So the direction is the same and the polarities are the same as above. The only thing we changed was the dots. And we want to see, do we get equivalent signs? The self-inductance is going to be the same. Look, I2 goes into positive, I1 goes into positive, yep. Or sorry, I2, I've got to be careful. I2 is leaving the positive, in fact, and I1 is entering the positive. So we get positive, negative, just like before. Now, let's just see if we're going to get consistent. Look at this. I2 is actually entering the dot, but V1 negative is touching. We still get negative, though. Look at here. I2 leaves and V1 positive touches. Both result in the same sign. Okay, what about for I1? I1 is leaving the dot, and V2 minus is touching the dot. So we have a leaving and a negative touching. We should still have a positive. Good. And what do we notice? Positive, positive, great. And look here, I1 enters, V2 positive touches is the same as I1 leaving and V2 negative touching. Good. We get equivalency. Yay. Okay. So I hope this is not too bad. Nice little introduction to ideal transformer relationships and mutual inductance equations. Let's look at a simulation, and then the next lecture we'll go into a little bit more detail into the ideal and then maybe some weird behavior, okay? Okay, let's look at the simulation. I'm going to share my screen and go to here. Okay, so let's look at this. What do we have? We have a transformer, and the transformer, you can determine the ratio. So this is N2 over N1. And you can specify the inductance and the coupling coefficient. So this is nearly ideal. Instead of being 1, it's 0.999. Okay, and this is L1, the primary inductance, right? Okay, so remember the mutual inductance is equal to K times L1, which is this one, times the ratio, which is that. Okay, so we're gonna, okay. All right, what else do we have? We have a voltage source, an AC voltage source that's going up to as high as 170 volts and down to minus 170. So the RMS should be 120. So this is plotting 120. What else do we have? I have a voltmeter, just expressing that, and a current meter, right? IP. So this is the primary current. This is the primary voltage. This is the secondary current, the secondary voltage. And I have my 2 dots here. Okay, dot here and dot here. Good. Notice I have it flowing into a 100 ohm resistor, 100 ohm resistor. Okay, so the ratio is 1:1, so I can reset this and just play and see what it would get. If we remember our ideal relationships, I should get the same voltage on the secondary as the primary, and you can see here pretty much the same, 120 RMS, 120 RMS. Here's a plot of both of the voltages on top of each other, and here they are kind of independent. Okay, slow this down a little bit. For the current, it's also 1:1. So you can see the currents are on top of each other, and here's the currents broken out. So they're both about 1.2 amps RMS. Okay. Now I can change the ratio. So let's make it a 2:1 ratio. And so that should make the secondary voltage jump. And I'll reset this and run it. And notice now the ratio of the secondary goes up to about 240 volts, which is double the primary. Now notice that the current goes down to 2.3 amps compared to 4.8 amps, right? So the voltage goes up, the current goes down. The current goes up, the voltage goes, right? The reverse is true for current voltage. They're inversely proportional, okay? Now look at this. You can see that the voltage of the secondary is in red and the voltage is double the primary. Here, the secondary current is in red and it's half the primary. I can flip it around the other way. I can go here, 0.5. So now it should flip. So actually the voltage will drop, but the current will double. Okay, and so let's reset this. And look at what we have. So now the secondary voltage is 60 volts RMS, so half, and you can see that here, it's half. But look at the current. So the current instead of is double, so 600 amps, or sorry, not amps, milliamps, whereas the primary was about 330 milliamps. Okay, and so now notice that the current is double, right? So this under ideal conditions is kind of showing us that that ideal transformer relationship is true. Now, the coupling coefficient is 0.999. It's not perfectly 100%, right? And the simulation actually won't let us put it at perfectly 100%. And so you can see, you get to see some weird things. So let's say you go to, like, let's say a ratio of 5, right? Do we still see a nice result? Uh, it looks kind of okay, right? You can see that the voltage of the secondary does increase, but it doesn't increase exactly 5 times. I don't think so, because 120 times 5 is not 480, it's 600, right? Okay, so you're seeing it's trying, but not quite perfect, right? What happens if I drop the primary inductance, right? 0.001, let's say. Let's try that. Do we get a nice behavior? Okay. Okay, we get maybe some nice behavior on the voltage, right? We get 600 now, right? And then we see that we get 6 amps to 552 amps RMS. That's weird, right? Let's hit a reset. Let's just see. So you're getting some weird kind of results, right? What else could we see? Let's see. Let's go back to 4, or let's go back to the ratio of 1 to 1. Do we get a nice ratio here? Reset. I hope we do. Good. This is the same. Good. You get some weirdness over here. And then let's go to something like 10. Let's see what happens if we go to 10. Do we get a 10 to 1 voltage jump? Okay, let's reset this. Okay, it's not too bad. It's not too bad, right? So we got 1 millihenry here, but you get some weirdness on the current, right? At the end of the day, what my point is that it's not just you can't just look at, even though the coupling coefficient is 0.999, you can't perfectly look at this ratio. There is some tuning that you'd have to do with inductance, okay? And there's also some relationship to this resistance. So if I drop this down to, let's say, 1 ohm, you get some weird things going on that we will talk about in the next lecture, right? But stay tuned, stay tuned. Oh, one thing we could do is just double check this. Notice I have an open circuit here. Obviously, the ideal relationship aren't holding, right? I have no current on the outside, right? And the outside would say the secondary is equal to N1 over N2 I primary. Well, obviously, in an open circuit on the outside, that's not going to enable that. What if we short circuit it? Okay, it's kind of the reverse, right? For the voltage, notice no secondary voltage. So those ideal relationships, V2 equals N2 over N1 V1 and I2 equals N1 over N2 I2, those are only under ideal conditions. So you got to make sure that you're not breaking those ideal conditions. Okay, well, this simulation, the link to the simulation will be in the description. You can check this out and play with different values of ratio, inductance, and coupling coefficient. You can play with different values of resistance over here, and even the max voltage on the source. Okay. I hope this was a useful lecture, and I look forward to seeing you guys in class. Have a great day.